All right, class. Welcome back to the regular lectures. Hope the midterm wasn't too bad for you guys. We still haven't finished grading the midterms. We should have them back to you by next lecture. Any announcements from your side? Okay, the next homework will be posted on Thursday, and so look out for that, and I'll make another announcement on Thursday. But office hours and everything else are back to normal this week. So I'll be holding office hours tomorrow at 10 a.m. Any comments about the midterm before we start the lecture? Was it easy? Was it hard?
Wasn't easy.
No? No comment? Okay. Nobody? Yes, Jason.
It's quite long.
It was too long. Yeah, I agree with you. I think that after looking at your solutions, no, I'm kidding. No, it was a little bit long. The good news about the midterm is I looked through it and it looked like, I've graded about half of them, and it looked like you guys understood the concepts, and that's good. That's really good. But there wasn't really enough time for you guys to execute. And that's the good thing about the final exam is you have more time. And I think hopefully we'll learn from our mistakes too and try to fine-tune the exam a little bit more. One of the things I wanted to just communicate to you guys is that if you have a problem on the midterm or final, there usually is a pretty easy solution, a pretty nice, quick, clean solution. If you find yourself deep, digging yourself deeper and deeper into algebra and complex solutions, and maybe you're going down the wrong path. The other just general comment I'll make is I noticed a lot of you guys will make mistakes that are very obvious to detect. For instance, the units will come out wrong. You're trying to calculate a voltage and you come out with voltage squared. And in cases like that, you should really, look at your answers. I get the sense that a lot of you maybe didn't have enough time to actually just look at what you've calculated and make sure it makes sense. Try shortcut approaches. When you're trying a problem, make a lot of approximations, get an approximate answer, and then check to make sure that that matches what your detailed calculation shows. For instance, the problem with a source follower, calculating the transfer function, of course the A1 coefficient should match small signal analysis. And you guys all know what the small signal gain of a source follower is. If your final answer didn't match that simple analysis, you probably did something wrong. So, always try to have checks and balances as you solve problems, as well on the homework and in real life too. Okay. All right, so let's get back into the regular lectures. Today we're going to talk about mixers. This is going to be an introductory lecture, so more of a systems perspective rather than a circuits perspective on mixers. So first of all, what is a mixer? I think by now most of you know what a mixer is. We've talked about them often enough, but let's just make it official. A mixer basically is a lot like a multiplier. So that's why we actually use a symbol for a multiplier for a mixer. And it's a 3-port device. It has an IF port. So this is a down conversion mixer. And the IF is the intermediate frequency as always. It has an LO port. The LO port is the local oscillator. And it has an RF port, which is the radio frequency port. So in fact, what I've drawn here is not an up conversion, but not a down conversion, but an up conversion mixer. And likewise, if I have the LO and RF comes in and IF goes out, this is a down conversion mixer. Yeah, that's a good point. Usually, if it's not specified, IF is usually lower than RF, but you're absolutely right. So IF is usually less than the RF frequency. Okay, so what does it mean? Why do we call it an up conversion versus a down conversion mixer? An up conversion mixer means that you start out at some lower frequency. So let's say low frequency. And somehow this mixer creates a high frequency signal. And as we'll see, it'll preserve the phase and amplitude modulation present in this low frequency signal, and it just changes the carrier frequency, so it moves it up to a higher frequency. And this performs the inverse operation. It takes a high frequency signal and converts it down to a low frequency signal, and that's why we call it a down conversion mixer. Now if you think about linear circuits, linear time invariant circuits cannot perform mixing, right? So a linear time invariant circuit is not a mixer. That's because a linear time invariant circuit cannot generate new frequency components that are not present in the input. And by definition, a mixer is doing that. So let's draw what a mixer does. So here's the input spectrum. And let's say I have a signal that looks like that. So this is the input. And then I'm going to draw the output over here. And basically, the output may look something like that. So this signal is moved up in frequency. So this is the up conversion process. In other words, if I look at the output, there's no frequency content, there's nothing at DC, right? And here there's nothing at RF, and yet there is RF signal. So this is the RF in this case, and this is the IF. Okay? And just a little bit of terminology. When a signal is centered around DC, we call this a baseband signal. And when the signal is centered around some carrier, or RF frequency, we call this a bandpass signal. Okay? And you can see that, in general, usually the course of events is on the transmitter we have an up conversion process, and on the receiver we have a down conversion process. So let's just first of all quickly review. Well, actually, let me not go there. Let me just say, to make a mixer, you need either a time varying circuit, so an LTV circuit, or you need a nonlinear circuit. Okay. Any questions up to here? Yes, Omar. A linear time varying circuit. We'll talk about that in this lecture. For instance, a switch is a linear time varying circuit. It's linear because it's a switch, but it can basically vary the circuit properties as you switch things in and out. Okay. All right, so let me just quickly review why we need mixers. Okay. And for that, I'll ask you guys to chime in. So why do we actually use mixers? Why are they useful? Yes.
Well, if you want to communicate in a broad or in a certain frequency, because you have, like, say, a certain frequency band, you need to mix up your signal.
Yeah, so basically we share spectrum, and one way to share it is frequency division multiple access. Okay. What are some other reasons why we use mixers? Okay, Omar?
Sometimes some frequency bands are better at specific medium than others.
Very good, yeah. So basically we mix because the propagation characteristics are better at certain frequencies. So for instance, I think I commented on this earlier, but earlier in the course we talked about how if you want to communicate at very low frequencies, you have to have very big antennas. Like for instance, the Eiffel Tower was used originally as an AM transmitter. If you want basically a mobile radio, you don't want to carry the Eiffel Tower with you, you got to go up to higher frequencies. Okay? Otherwise, your radio is going to be very inefficient at propagation. Okay? There's also, this spectrum sharing, there's two components to it. There's also the FCC. So we're just not allowed to transmit at any particular frequency. In the United States, the FCC tells us that for a certain type of communication, you need to use a certain frequency. And so the mixer is used to move the information to that frequency. Okay? What are some other reasons for using mixers? Yes?
Yeah, it might be easier to process the data at lower frequencies rather than at the RF frequencies.
Yeah, so that would be why we would down convert, right? So basically, IF, let's just say IF stages needed for signal processing, RF stages needed for propagation. Okay? Any other reasons? Matching? How so? Can you use the mic? Thanks.
If we have an amplifier that works at 10 gigahertz and our original data is at maybe 1 megahertz, if we use an oscillator, then we can get better gain.
Okay, I think what you're saying is more or less the same as this point here, right? That we signal process at certain frequencies and then we like to transmit at different frequencies. All right, anyone else? Well, another reason that's a little more subtle is stability. And it turns out that in a radio receiver, you need a lot of gain. You might need 100 dB of gain. And if you've ever built an amplifier with 100 dB of gain, you know that it's very easy to build also an oscillator. That any parasitic feedback back to the input causes the system to oscillate. Or if you use a mixer, you have gain at different stages. So for instance, I might have a couple of amplifiers, let's say at 2 gigahertz, that's my input. And then I mix down to, let's say, 500 megahertz, and I have some more gain, and so on and so forth. And the idea now is that if there's coupling from here to here, this is not in the passband of this amplifier, and so it will not cause stability problems. So it's a lot easier to design a high gain stage, amplifier stage, if you have different frequencies present. Okay, make sense to everybody? All right. Well, let's look at an ideal multiplier and see how it acts like a mixer. So an ideal multiplier, let's say we have our RF signal, and I'll call it A of t cosine omega naught t plus phi of t, where A of t is the amplitude modulation and phi of t is the phase modulation. And as we'll see later in this lecture, more or less any kind of signal that we transmit can be represented in this form. It has some amplitude modulation component and some phase modulation component. It could be an FM signal, an AM signal, a digital QPSK signal, a QAM signal. This is a pretty general representation of the signal. You could break it down into amplitude and phase modulation. And for our LO signal, let's take a constant amplitude signal and constant frequency signal. And let's just take the multiplication. So I'm going to calculate VRF times VLO. Okay? Now, let's use a trigonometric identity that if I take the cosine of a sum, I get cosine of each individual angle minus the sine of each individual angle. And if we apply this identity to this multiplication, so I have the output, which is the, let's say, VRF times VLO. The amplitude is A of t, A of LO, divided by 2, cosine phi times, well, let me actually simplify things for now. Let's just forget cosine of phi for now, just to make life simpler. So I have cosine omega naught t times cosine omega LO t. Okay, and applying this identity, I could say that cosine A cosine B is equal to, let me come back here and plug in cosine A minus B. These pens are pretty dreadful. Okay, and cosine function is an even function, so these terms stay the same. And sine function, though, is an odd function, so here I get sine of A, sine of B. And if I take the sum of these two terms, you'll see that these terms cancel out, and I get 2 cosine A cosine B is equal to cosine A plus B plus cosine A minus B. Okay? And so if I substitute that over here, I get A of t ALO divided by 2. That's the 2 I was putting in. And then here I would get the sum frequency, cosine omega naught plus omega LOT plus cosine omega naught minus omega LOT. Okay? So very simple algebraic manipulation shows us that multiplying two signals together, basically all it did was it took our original input tone, so this is the input, and it moved it to a new frequency. So this is the what we call the upper sideband, and this is the lower sideband. So let me draw a picture. So this is our tone at RF, and this is our tone at LO. And what we see is that when I do this multiplication, I get 1/2 A of t ALO at some frequency, RF plus LO, and some difference frequency. So this is LO minus RF. So this is the upper sideband, this is the lower sideband. Okay? Questions? So we see that actually an ideal multiplier is both an up conversion mixer and a down conversion mixer, right? It created a tone at lower frequency and at higher frequency. And so really to build a down conversion mixer, I would just put a filter here. So if I take an ideal multiplier, take my RF, take my LO, and then go into a low-pass filter, this is basically a down conversion. On the other hand, if I do the same thing, and I have a high-pass filter, it's an up conversion. All right? And also, if you do the analysis a little more carefully, you can, we just did it for a tone, you can show that if you have an arbitrary modulated signal that has some spectrum, then the action of multiplying it by a tone is to basically move that spectrum of information to these different frequencies. And actually, these should have the same amplitude unless there's filtering present. Okay. Now, one way to think about this is multiplication in time is equivalent to convolution in frequency, right? So what I'm doing is I'm just sliding this spectrum past here. When it hits the LO, I generate basically this tone. And then you might say, well, where is this tone coming from? Right? Anybody know where this tone's coming from? If I do a convolution of this with this, exactly, right? I also have a minus LO. So if I look back at my signal, if I have cosine omega LOT, this is really e to the j omega naught t plus e to the minus j omega naught t divided by 2. So there's actually 2 tones here. All right. Questions? All right, so one of the problems with a mixer is what we call the image problem. Even an ideal mixer, the ideal multiplier, okay? So let's look at the image problem. Let's say I want to build a down conversion mixer. And let's say the spectrum looks like this. So let's say this is my LO, and this is my RF, and I down convert this to, so this is DC, and this is my IF frequency, which is really this difference here. So I want to down convert my information to this frequency. Okay. Now if you think about a mixer, what it does is I could have injected my LO either below the RF or above the RF. It doesn't make a difference. The only thing that matters is this difference in frequency. So in essence, any energy which is within one IF frequency of the LO tone in an ideal multiplier gets down converted to the same IF, right? So if I had, let's say, some information here at the image frequency, and let's say it just happened to be noise, then this noise also gets converted down to this frequency. Okay? So best case scenario, the noise in the image band is also going to get converted to my IF frequency. The worst case scenario is that you actually have an interferer in your image band. So you might have a huge interfering signal that would also get converted to the same IF and pretty much overwhelm your input signal. So this would be considered a distortion component. This would be your signal, and your signal would be below the distortion, and so it would be very hard for you to actually detect what was being transmitted. Okay? So the key point is that the mixer converts energy at LO plus or minus IF to IF. Okay, any questions about that? Okay. So here, let's just do a quick example, a numerical example. Let's say that our RF signal is equal to 1 gigahertz or 1,000 megahertz. And let's say we want to go to an IF of 100 megahertz. Okay? So let's say we select our LO, right, to be the difference. Let's say we select 900 megahertz. Okay? Well, that means that my RF, which is 100 megahertz away from my LO, gets down to IF, but my image, which is 100 megahertz below 900, or at 800 megahertz, also converts down to 100 megahertz IF. So I have to be aware when I design a mixer that I'm not just moving my desired signal, but I'm potentially moving this image signal. In some cases, I may know what the image band is. I may know that nobody transmits in the image band, and so I'm okay. I can actually not worry about it. In other cases, the image band may actually be another channel in my system, or it could be some spectrum that I do not own, so I don't know what's going on in that spectrum. Okay, so this is a very important point. So the image is very important, and it's something that we're going to return to over and over. Okay. Now, what's a simple way to deal with this image problem? Yeah, filter, right? Why can't I just filter? So in this example, my signal is at 1 gigahertz, and my LO is at 900, and this is the image at 800. So let's say I had a filter, very sharp filter, that basically rejected any energy coming in on the image band. Then, even if there's an interfere here, I knock it down, and then I just process my signal at RF. Does that work? Yeah, it actually works. This is a simple way of solving the image problem. So, kind of a classic receiver looks like this. A classic receiver has an LNA, and then it has a filter, and then it goes to a mixer. So this is called an image reject filter. Okay. And so at the input now we can have the RF signal plus potentially an image signal, and only the RF signal will survive down to IF. The image signal will get rejected by this filter. Okay? And of course here I would put maybe a low pass filter to select my down conversion product. Okay? Questions? The image, as I said, it could be anything. It could be somebody else sharing the spectrum with you, right? We'll do a couple, like in this example I just did, right? I'm using 1 gigahertz, and there's an image at 800. Now, 800 happens to be a very popular frequency band. Everybody and their mother is transmitting with their cell phones, right? So, if I'm trying to do a really sensitive radio link, and I don't filter against 800, then the whole 800 megahertz band falls into my baseband. And so it's going to be very difficult for me to to actually get useful information out. Okay? Yes.
So in this example, you can place LO either at 0.9 gigahertz or 1.1 gigahertz, I guess.
Yeah, but the problem doesn't go away, right? Because then 1.2 gigahertz becomes the image.
So in general, any pros and cons of where you place LO?
Yeah, so that's a good question. So let me just repeat the question in case you didn't get it. So here I picked 900, right? And 800 happens to be a very bad image band. So you might say, well, why not pick 1.1 or 1100 megahertz as my LO? So this is LO2. And this would also down convert to 100 megahertz, and it would move the image band to 1.2. Sorry, this is getting bad to write on. So in other words, I could have an LO frequency above my RF or below my RF. And which is better? It depends. A lot of people would say it's always better to lower side inject because it's easier to build a lower frequency LO. It takes less power. That's not really true. It depends a lot on the radio architecture. As we'll see, it depends a lot on the IF frequency. And usually the choice of upper or lower is dictated by basically the planning of a receiver or whole transceiver, the frequency planning. You have to make sure the frequencies don't overlap and there's good isolation, and it's something we'll talk about a little bit more. Yes?
Exactly how would you do a down conversion as opposed to an up conversion? Like, what's the difference with your LO frequency? Do you just multiply by the cosine, or?
No, so as we said, the ideal multiplier produces both sidebands, right? It produces a lower sideband, the difference frequency, and the sum frequency. And the only way to make it work is to filter. So that's why here I put the low pass filter to select the beat frequency or the difference frequency.
Well, I mean, if you're dealing with your own signal, right, then you're transmitting, so if you're up converting you to say 900 megahertz with your LO, then you have a signal at 800 megahertz and at 1 gigahertz, right?
Let's actually take your example. Let's say we're going to build a whole system. Okay, so basically I have my information coming in, I mix it, I filter, and then I would go through a power amplifier and I would transmit it. Okay, so this is my IF. Let's say this is your voice in a classic analog system. I upconvert it. Let's say that my voice has a bandwidth of 10 kilohertz. Okay, and so I'm going to upconvert that to, let's say, 1 gigahertz. So here I transmit at 1 gigahertz. Okay, so roughly my LO is about 1 gigahertz. And so the output is going to be, so basically if I take 1 gigahertz and mix it with 10 kilohertz, I'm going to get the sum and difference frequency. So I'm going to get, this is 1 gigahertz plus 1 kilohertz. This is 1 gigahertz, or sorry, 10 kilohertz. This is 1 gigahertz minus 10 kilohertz. Okay? And so you see you have an upper sideband and a lower sideband. This is the difference frequency, this is the sum frequency. And here I would, in this very simple scheme, I would actually select one of the sidebands. The reason I don't transmit both sidebands is that there's redundancy. It's the same information, so I would be wasting bandwidth if I transmitted both. So then I would have maybe a filter. So this would select the upper sideband, and I would transmit that signal. That makes sense? Okay, so there's an issue with the filter design that has a lot to do with the choice of the IF frequency. Let's take another example. Let's say again we have an RF of a gigahertz, and let's say our IF is 1 megahertz. Okay, let's say we're doing a kind of a low data rate or medium data rate system, and we have on the order of, let's say, 5 megabits per second of data, and we choose an IF of 1 megahertz, or a bandwidth of 1 megahertz. Okay, so the image is basically 2 times IF away from the RF. And in this case, because the IF is rather small, right, 2 times the image frequency is actually pretty small. So if this is my RF, this is my LO, this difference is the IF, and the image appears exactly 2 IF away. So this is an IF and this is an IF. So this is 2 IF. And if I have to build a filter that has, let's say, flat characteristics in band and then lots of rejection, if the distance away from basically the cutoff is very small, it's hard to get a lot of rejection, right? You have to have a very high order filter. If this were a simple one-pole filter and I just moved 2 megahertz away from the passband at a gigahertz, I would practically have no rejection. So in order to get a lot of rejection, it means I have to build a very steep filter. So this requires okay. And just for fun, I went online and found a filter synthesis program, and I said, let me try to synthesize a filter that actually can give me a lot of rejection. So what I did was I went and did a filter synthesis. I did a 5th order Chebyshev with 0.2 dB of ripple in band, and I was able to get 80 dB of rejection at the IF frequency. Okay, That's pretty good, right? 80 dB. I can knock down an interferer by 80 dB. Question?
If we add more pulse, doesn't that mean our phase shift is going to be worse?
Okay. We can do a whole lecture on filter design and group delay characteristics and phase distortion and amplitude distortion. For now, let's just say we don't care about that. In other words, the signal is very narrowband, right? And so within a small frequency range, we don't expect too much distortion to occur. Okay. The point I want to make is that this filter is extremely hard to build. Why is it hard to build this filter? Anybody? Well, think about a simple second order system. Because we really build our filter out of cascades of second order systems, right? Maybe you haven't studied filter design, but you know, the simplest filter that you already know how to build is just a LC filter, right? So if I build an LC filter, what's the relationship between the quality factor and the bandwidth, right? I know the quality factor is omega naught divided by the bandwidth. Okay? And so in this case, I have a center frequency of 1,000 megahertz and a bandwidth of 1 megahertz. In other words, the quality factor is 1,000. And go out and search. As hard as you try, you will not find inductors and capacitors with quality factors of 1,000 at a gigahertz frequency. So you basically, it boils down to, if you try to build this filter with passive components, you won't be able to do it. Okay? So then you say, okay, I can use active components. I can use essentially transistors to overcome the loss in the filter and effectively build really high Q filters. Most of you probably haven't studied that. Some of you have been exposed to it. But it turns out that if you build an active filter, you're going to have some problems. First of all, in active filters, where you use transistors, essentially you use transconductance stages, you need the active devices to operate much faster than the frequency of operation. In other words, their FT should be a factor of 10 better than what you're trying to operate at. So if you're trying to operate at a gigahertz, you need transconductance stages that operate at 10 gigahertz. You can do it, but you're going to need the best process in the world and pay a lot of money for it, and it's going to burn you a lot of power. It's going to cost a lot in power as well, power dissipation. The other problem, what's the other issue with active filters? So let's just say passive filters can't do with LC because you can't get the Q is too low. With active filters, the issue is going to be power dissipation, process. You're going to need a really expensive process. And linearity. Whenever you put amplifiers into your filter, it's going to be nonlinear, and we'll see that that can actually make the problem worse. It can generate distortion products that are worse than the image. So the upshot of this is that choosing the simple IF of 1 megahertz is probably not such a good choice. Okay. Now there is one way that you can buy. Okay, I lied. You can buy this filter, but it's going to be basically a SAW filter. So I'll say you need non-IC technology. So people have designed, there's tons of companies out there that design high Q filters with materials like, so basically one common high Q filter is called a SAW filter. It stands for Surface Acoustic Wave Filter. And you're essentially using material properties to build filters, not L's and C's. So you're building mechanically resonant structures. So mechanical resonant structures. And these can have extremely good high high quality factors. They tend to have insertion loss, so relatively high insertion loss. And they're actually bulky. That's the biggest problem, is they're really bulky. And and the other problem is that the impedance levels are on the low side. Okay, so let me go through these points and point out. So let's say that you build your radio, the one we just described. So you have your LNA, and the LNA is on chip. So this is the chip boundary. And then you have to go off chip into this filter. So this is our SAW filter. And for instance, the SAW filter might be designed with an input impedance of 50 ohms and an output impedance of 50 ohms. And then we go into our mixer. Well, just the fact that we have to come off chip is a big pain, right? Because I didn't draw this to scale, but this is, so not to scale. But, you know, the real scale looks something like this. This is our chip, and then the filter is like that big. Okay? So it's bulky, and you know, it's okay if you're building one radio, but today we're in a situation where, you know, simple cell phone might have 5 radios in it, right? And you don't want 5 of these filters to take up all the board space. They also tend to be more expensive. Okay. The other issue is this impedance. So if you design this, if you could get rid of this filter and keep the signal on chip, turns out that you can keep the impedance levels much higher, especially at low frequencies. You might be able to drive the input of the mixer at a couple hundred ohms, or maybe even higher impedance, 500-600 ohms impedance. If it's a good process, you have high quality inductors. Coming off chip, though, you have to go to 50 ohms, which means that you have to drive a lot more power to go off chip. So it tends to basically increase the power dissipation. So if we could avoid this, we'd certainly like to do that. All right. Now, what is happening in the research community is MEMS filters. Okay. And these are basically, again, mechanical structures, but these are mechanical structures that you can integrate on chip. So MEMS filters may actually save the day. You might be able to take this filter, put it on chip, reduce the size considerably, not have to come off chip like this to drive the extra pins, inductance, or low impedance, keep the impedance level relatively high, and have a really high performance system. But today, it's only in the research community where you can actually build these filters and make them work. You can't actually go and commercially get access to these kinds of technologies. Okay.
So the F bar is not commercial.
Yeah. So F bar is commercial. So there's the F bar, and let me see. This is a bulk acoustic resonant mode. What does the F stand for? Thin film? Can't remember what it stands for. But F bar filters are commercially available. So. But it's not IC compatible or silicon. So you still need 2 chips. So you might have a silicon chip, and then you have your F-bar chip, and you have to bond to it and put the filters in here. Okay. There's some research activity, bulk acoustic wave filters that are basically integrated on chip, on top of the chip. So you have your silicon chip, and then on top of it you put your BAW filter chip. But you know, this is research, and probably in a year or so it'll be available. But as we'll see in this class, there's other ways to solve this problem. So that solving the image problem with filtering is the classic solution. And we'll see that a lot of people have moved away from that. It's actually probably the best solution in terms of robustness, but because of the fact that it has to be integrated, it can't be integrated. It's a problem. Okay. So let's see if there's a simple way to solve this problem. So let's do a two-stage IF. So instead of down converting directly to 1 megahertz, let's down convert into an IF let's call it IF1, and then let's do another image reject, and then down convert into IF2. So this will be LO1, this will be LO2. And again, let me choose. So let's say this is a gigahertz. Let me make my IF 100 megahertz. Okay. So then this will be my RF, and this will be my image. So now the distance between the RF and the image is 200 megahertz. Okay, now the filtering problem is relaxed, right? It's not as tough. Now the Q factor is about 10, and that's reasonable. That's something that I can build. And so what I've done is I've simplified the Q factor. I've lowered the Q factor considerably by just having a two-stage process. And now the second stage, of course, will go down to 1 megahertz. And again, if I put my LO at, let's say, 99 and my image is at 101, it's still not too bad. It's still doable. Q is a little bit higher. You could go for another stage to make it even simpler. But simply picking a reasonable value of IF, not too low, makes the problem a lot easier. Okay? So higher IF frequency relaxes Q of filter. Any questions about that? Does that make sense? In fact, even this is aggressive. Let's say I had selected an IF of 500 megahertz, right? Then my image would have been at 1.5 megahertz, and it would be really easy to filter that. In fact, I could just use a low-pass filter. So, let's say, so this is 1 gigahertz again. I'm going to use a 500 megahertz IF. So 1.5 gigahertz is the image, and this is my RF signal. Sorry, 1.5 is my LO, and 2 gigahertz is my image. So let's say you have a big interferer. At 2 gigahertz. Well, now I can have actually a relatively simple low-pass filter which will knock down my interference quite a bit, and I get rid of the image problem. Yes?
Don't you lose half the power each time you mix? So when you go for multiple mixing stages, wouldn't you lose your power each time? Because you go to LO minus RF and LO plus RF. And
yeah, so what we'll see is that when you build mixers, you can actually build mixers with gain. It's very easy to put gain in a mixer. We'll see that when we actually design it. So that's not necessarily a problem. But even if you were losing gain, you can build passive mixers. They're used mostly at really high frequencies. You can always put gain after the mixer, right? It does, right? It will have an effect. But remember, the further down you go in the chain, the less important the SNR is, because you've got all this gain in front of you. Okay? Any other questions? Okay, in the back.
Why do you start the corner frequency of the low pass at RF instead of the IF at 500 megahertz?
Because remember, this filter comes before the mixer. Yeah. Okay, well, another approach that's very popular is called direct conversion. Or also zero IF. Or I should put the quotation marks around zero. So what is direct conversion? Direct conversion means that you make your LO equal to your RF. So you actually, in one shot, down convert everything to an IF of DC. Sounds really good, right? Very simple. Why mess around with all these IF stages? The whole problem of the image is because your IF is basically, you could say that your IF is, your image is 2 IFs away. Well, if your IF is 0, you are your own image. And so then the image problem goes away. Okay, so it seems like a really good solution. So what are some of the problems with this? It's interesting, if you look at the history of radio design, the earliest inventors of radio clearly recognized that this was a good approach. But it took something like, I don't know, 70 years or 80 years before people actually started using this. That's because there are actually a lot of problems with this architecture. So what are the problems? Okay. All right. Okay, so yeah, so one thing that you bring up is it hard to match the LO to the RF? Well, in some ways, no. We always have a good frequency reference in our radio. It's usually a crystal oscillator. We'll talk about crystal oscillators later in the course. So from a frequency resolution perspective, we can build very good crystals that are very well matched. And even if you didn't have a crystal, you could think of sending a pilot tone and using a phase lock loop to detect the frequency that's being transmitted. So in theory, that problem can be solved. Okay. All right. So what are the problems? Okay. So let's talk about even order distortion. And the LNA and the mixer. Okay. What happens to, can you guys now see what the problem is? All right, think about your nonlinear distortion analysis. If you have even terms, what do even terms generate? Exactly, they generate DC. So even order terms generate DC. And for small signals, the IM2 is the biggest component. But even if I just put a big signal in here, right, if this is cosine omega naught t, and this is cosine omega LOT, if I take the product, I get 1 plus cosine omega naught, this is also omega naught, 2 omega naught t divided by 2. So this is the DC term, this is the desired down conversion, but, and this is the second harmonic, which we filter, that's no problem, we put a nice filter here. But if I just put in an RF signal, and this thing is, so RF comes in, and let's say this is an x squared, has an x squared term. Then I know the x squared term also produces 1 plus cosine 2 omega naught squared divided by 2. And so this is a DC error, right? So this is a distortion term. And this gets mixed, so it may or may not appear at the output depending on our mixer, but then the mixer also generates even order terms. So it will also generate terms that compete with our signal. And so the biggest problem for, one of the first problems for direct conversion is that there's lots of errors being generated at DC. Okay? So one potential solution is to AC couple. Right? In other words, if I have my information at DC, maybe it's okay if I just take out a little bit of that information, or I can even create a modulation scheme that doesn't generate any data at DC, and then I can AC couple stages. So I can have my mixer, and then I AC couple it into my, let's say, my VGA and my other stages. What's the problem with doing something like this? Do the same thing with my LNA.
Knocking out the useful information.
Yeah, but let's say that's okay. Let's say that I've designed my system so I can tolerate that loss, or there's no real information that's coded there. Okay.
Is it a very big capacitor because you're dealing with low frequencies?
Yeah, it's a huge capacitor. Okay. What are some other problems?
Stability?
Well, huge capacitors usually make things stable, right? They filter everything out. But it's settling time. Huge capacitors take time to charge and discharge. So if I had some kind of spike signal come in here and then disappear, let's say I had a big interfere, it appears, generates lots of even order distortion, and charges up this capacitor. That's great, the capacitor rejects that, but then let's say it disappears. So now this capacitor has to discharge. And let's say it takes 10 microseconds to disappear. Well, during that whole 10 microseconds, you've got this discharging current, the settling time, which is actually producing errors at baseband. Okay. Okay. So this is AC coupling. Another problem is LO leakage. So if I have my LO signal, let me just say one more. Okay, I'll come back to that. So I have my LO signal, and this is my antenna, and this is my RF, and my LO is equal to my RF, right? That means that, if I build an amplifier, ideally it has no reverse gain. All the gain is in the forward path. But any real amplifier has some finite attenuation in the reverse. So this signal will leak and get to my antenna. Okay? This is a fact of life. Actually, if you build any receiver, there's always a finite amount of LO leakage. And so you might say, okay, what's the big deal? So you leak a little bit of LO into the RF spectrum. Well, the problem is that this LO doesn't just perfectly radiate. Part of it comes back and mixes with itself. Okay? So if you think about this from like a wave perspective, there's a little transmission line going out to your antenna. Your antenna is not a perfect impedance match, right? It never is. So part of that signal is going to reflect. And so that part of that signal, so some small fraction of the signal leaks, hits the antenna, it reflects, and then it goes back into my amplifier, gets gained up again, and appears as an input to my LO. So what happens when I mix LO with LO? So the LO self-mixes and produces DC. Okay. So LO leakage also creates energy at DC, which could interfere with our signal. Okay, again, if it's just a DC term, you can use a blocking capacitor, right, and get rid of it. But it's more complicated than that. First of all, let's say I didn't use a blocking capacitor. What might happen? I could actually rail my baseband, right? If there's a DC offset that comes in and it's 50 millivolts, and I've got 80 dB of gain, right? That's going to rail my baseband stages. So I've got to get rid of that. So I've got to either AC couple, or I've got to have some kind of circuit that detects that DC and subtracts it out at the input. Okay. Well, the problem is that it's not strictly DC. It actually is time varying. Why is it time varying? Anybody want to take a stab at why you think it might be time varying? Yes, Christian.
Is it because of oscillator phase noise?
That's part of it, but let's not talk about phase noise right now. So it's going to have a phase delay with respect to itself, sure. But why would that phase delay vary? But why would it be varying as a function of time? Sure, temperature changes will cause variation, but something a little more practical. Something basically more alarming. Yes?
Is the apparent gain of the amplifier changing?
It could, right? You could have interference signals and that, so basically you see there's a lot of reasons why this signal can change. One of the biggest reasons it changes is, remember, we're talking about reflection off the antenna. Antenna impedance is not constant. As you move the antenna around, right, as objects come near the antenna impedance changes. And so this reflection coefficient highly depends on the environment that the antenna is interacting with in its near field. So the amount of LO leakage that leaks back and self-mixes depends a lot on the environment, which is an unknown factor. And for instance, if you bend your antenna, or if you lean your head, you're sitting on the bed talking on the phone, and you lean over, your head is a conductor, and it changes the amount of self-mixing in a direct conversion receiver. Okay, what other problems do we have? So I'm trying to convince you guys, first of all, that this is a bad idea. And then I'll convince you that it's a good idea. So we're in the bad idea stage right now. What are some of the other reasons why it's a bad idea, Omar?
If you have a really broadband signal and you want to directly convert it, and say it's in a low frequency range, then second and third harmonics of the LO might fall in band.
Okay. I'll repeat what you said because you're not using the mic. But so you're saying if you have a broadband signal, and the second or third harmonics of the LO signal could also mix with it? We're talking about, for now, let's say we have a perfect oscillator, just one tone, and a perfect mixer, just a multiplier.
Oh, in that case, then you're fine. But
Actually, you. Yeah, well, we'll talk about that later. But actually, what you bring up is interesting. If you do have a broadband signal, there is a problem. In fact, I was hoping you'd talk about this. So if I have a direct conversion system, you can see that there's not much gain at so-called RF, right? You might have an LNA, maybe it has 15 dB of gain. Maybe your mixer has 10 dB of gain. So you have only 25 dB of gain. So now you're at baseband, you have some filter, and then you're going to have basically, you're going to need a lot of gain to take the signal, in the worst case, from a tiny signal, let's say coming in at minus 100 dBm, to a signal that you can actually put into your ADD converter, which is a respectable signal on the order of, let's say, tens of millivolts. Okay? To get from microvolts to millivolts, you're going to need a lot of gain. In fact, you may need something like 80 dB of gain out of these stages, right? Now, if the signal is very narrow band, that's fine. This is basically an amplifier. Let's say the corner frequency is 100 kilohertz. No big deal. I can design an amplifier with a gain of 80 dB and 100 kilohertz bandwidth. But let's say now I say my signal's 100 megahertz, right? 100 megahertz, 80 dB, that's pretty challenging. Okay, so you do bring up a good point, is for broadband signals, gain bandwidth product can be challenging at IF stages. Okay.
But just a short question.
Yes.
How is this related to the direct conversion now? I mean, the broadband, I always have the problem no matter where my IF sits, right?
Okay, yeah, how this relates to direct conversion is if I had an IF that were, so let me now do an alternate system. So I have system 1, which is direct conversion, and I have system 2, let's say, that has a couple of IFs. And looks something like this. So here I might have 10 dB, again 5 dB here, and let's say I have 20 dB here, right? Another 10 dB here. Let me make this 15 and 10 to make it more realistic. So you can see that I've got gain here spread out. It's not all occurring at one frequency. And these are basically bandpass systems. So for instance, if my first, let's say that the input signal is coming in at 10 gigahertz. Okay? And let's say my first down conversion is at 5 gigahertz. And let's say I have 100 megahertz of modulation. Well, 100 megahertz at 5 gigahertz is still narrow band, so I can use LC circuits. And that can be a lot lower power than here, where I need 100 megahertz bandwidth and 80 dB of gain. That makes sense? Okay. All right, so what are some other problems with direct conversion?
1 over F noise.
Yeah, thank you. 1 over F noise. It's a big problem. Because, again, keep drawing this over and over again, we're going to need basically lots of amplifiers at DC. And in this class, up to now, we've only talked about RF. And at RF, we neglect 1 over F noise. And if you look at the noise spectrum of a transistor, let's say I'm looking at the drain noise of a transistor, the spectrum looks something like this. This is the thermal noise. And then there's this noise corner frequency. This is the frequency at which the flicker noise is equal to the thermal noise. And this is very process dependent. Let's say that our process has a corner frequency of a megahertz. Then below a megahertz, the noise climbs up at a rate roughly like 1 over F. And you might say, well, how long does this keep climbing up? Well, experimentally, people have even looked at, for certain technologies, down to a hertz, and you still see the thing climbing up. Subhertz, 0.001 hertz, it's still climbing up. So this noise is getting worse and worse at low frequencies. And so if your circuit is operating in this region, it's going to have a really high noise figure. And so your modulation your signal better be a lot larger so that it can compete with this 1 over F noise. Okay? All right, very good. Yes?
Wait, so what is the F, and so where does that come from, the noise?
I don't know. It's very complicated. So if you read papers about 1 over F noise, usually they're attributed to traps. Basically, if you look in the oxide of a MOSFET, because the oxide is near the surface, they're so-called dangling bonds, so incomplete bonds between silicon dioxide and silicon. These create energy states that can trap carriers and release carriers. It's a random process. There are also traps inside the oxide, and so electrons that are near the surface can interact with these traps. And the summation of all this interaction, if you look at this noise process, it has a 1 over f spectrum. But 1 over f is actually pretty universal. A lot of different noise processes lead to 1 over f spectrum. So resistors have 1 over f noise. A lot of different things in circuits actually do have 1 over f noise. Bipolar transistors have 1 over f noise. So bipolar transistors are basically kind of bulk devices. And they're basically, the interaction doesn't occur at the surface. So maybe I can draw a picture. So this is a problem especially for CMOS. The reason it's a problem for CMOS is that in a CMOS device, all the action is occurring right here at the surface. So our channel is basically next to surface. And the surface has all these interface states that cause 1 over f noise. In a bipolar device, this is the base, this is the emitter, and this is the collector, the subcollector. And so the actual transistor action is happening here, away from the surface. And so you don't have 1 over f noise. So BJT devices have much better 1 over f noise. Okay. All right. Just a side comment. Now I've told you guys how terrible direct conversion is. If you go out there and look at real systems, you'll find that there are actually a lot of real systems that are direct conversion. And they've basically systematically have solved all these problems that we've talked about with good engineering, like tricks you can use to make circuits operate with lower 1 over f noise. You can basically do really good layout, use differential circuits to minimize even order distortion. So you can play lots of games to build really good receivers and then build direct conversion receivers. In fact, Al Molnar, your GSI, I think probably one of the first cellular direct conversion receivers. He was responsible, his group at Connexent designed one of the world's first direct conversion receivers for cellular communication. And it was a feat of engineering, right? It was not trivial to solve these problems. Yeah. I'm sure he has some good stories for you guys during his lecture. Okay, so let me say another thing about direct conversion. Let me just point out something very simple. Let's look at the phase of the LO versus RF, right? So when we considered my RF signal, I said it's a cosine, and I said, oh yeah, my LO is also a cosine. Okay. So this is my RF amplitude, this is my LO amplitude. So when I take the product, great, I get 1 plus cosine 2 omega RF t, so this is also at RF, divided by 2. Okay? And this is the information. Well, what about, who says that these are in phase, right? They could be completely out of phase, right? They could be 90 degrees out of phase. So this could be ALO sine omega RFT. And this is now cosine. Well, what happens when I multiply sine times cosine and I take an average? Get 0, right? So already you get a sense that direct conversion is not as simple as you thought. Okay? If you do look at it a little bit more in detail, you'll find that actually it turns out there is an image problem. Okay? And the image problem comes about because if you take a signal, if I draw my signal, any real signal, of course, has to have an even spectrum.